I'll continue. I start again. First of all, thank you for inviting me to this conference call. I'm CoCo Enriquez, Mechanical Engineering, working in Iberdrola, Engineering and Construction in Nuclear Division since 2007. I'm also developing my PhD since 2011 in Technical University of Madrid about the strategies for direct steam generation in solar power plants, mainly focused on linear solar collectors. This thesis is being developed at the Thermoenergetic System Modeling Researching Group, whose main responsible are José María del Bar and Javier Muñoz. My presentation will deal about the comparison between two software tools, SAM System Advisor Model and Thermoflow for linear Fresnel power plant design. Next slide, please. In this first slide, I summarize main issues to develop during my presentation. A brief introduction about both software tools, Thermoflow and SAM. Solar field modeling main capabilities in both solutions. Balance of plant modeling main capabilities comparison. Linear Fresnel reference power plant case selected to make the comparison. Design point results. Annual performance plan results. SAM and Thermoflow capabilities summary. And finally, the conclusion and proposed future work. Next slide, please. Thermoflow is a graphical, next slide. Thermoflow is a graphical, fully flexible environment, very user-friendly to model a design a broad range of mass and heat balances in power plants. This tool was originally developed for gas turbine plant design, and recently in 2009, in Solar Spaces Conference, was presented as a tool integrating design, simulation, and cost estimation frameworks for solar plants and cycle design. Next slide, please. SAM is considered a primary key reference tool developed by U.S. Department of Energy for designing concentrated solar power plants and other renewable energy solutions. SAM integrates very reliable technical performance models. Also, a quasi-steady-state model to estimate annual plant performance is available, based on an innovative stochastic methodology to calculate BOP energy production. This final result is reducing computing time and provides a very quickly design approach. In relation to the economical and financial simulations, SAM developed a detailing financial and economical models providing very confident final renewable energy prices and costs, including U.S. government incentive and tax to deploy new renewable solar plants. Next slide, please. Solar field modeling main capabilities, comparison. Meteorological data loaded from weather files. SAM provides this option and also it links to official web pages for different countries' weather data information. However, Thermoflow doesn't include it, but integrates a model to estimate the fraction of sun radiation flux reaching the Earth at a specific location. Solar field configuration modeling flexibility. SAM developed two alternatives for solar field configuration modeling, recirculating parallel loops or one-through loops for configuration alternatives. Thermoflow provides a more flexible graphical simulation environment for solar field configuration design, showing extreme properties like mass, pressure, temperature, enthalpies, details between solar field components and balance of plant components. Header and receiver pressure drop models. SAM calculates pressure drop models by means of fixed coefficients. Thermoflow includes more accurate models. Saturated steam pressure drops are calculated with Friedel correlation. Superheated steam and supercritical water are considered compressible fluids, talking about the point of view of pressure drop calculation methodology. Receiver thermal losses. Both software integrate the capability to calculate thermal losses based on empirical polynomial equations provided by manufacturer. In this case, and in this study, Novatec. But Thermoflow also includes a very accurate model with Candica and Ditus-Bolter correlation for liquid and superheated steam heat transfer coefficients, calculation, and receiver pipes. Next slide, please. Solar field operation limits. flow limit to avoid stratified flow inside receiver and to guarantee annular flow under low radiation levels are provided by means of sun incident angle limits to stow and deploy collectors. Also, heat transfer fluid freezing temperature limit can be set by user, and a stow wine limit to avoid mechanical damages in collectors. All these parameters could be input by some designer, but are not available under Thermoflow environment. Solar collector and losses factor. Thermoflow explicitly calculates the solar collector and loss factor based on the following equation. And this equation is based on three variables. The first one is the distance of primary mirror from the tube absorber. The second one, the receiver length, and the last one, the longitudinal incidence angle. Some consider and losses factor included in incident angle modifier values, as detailed in Novatec commercial brochure. Solar field thermal inertia. Thermoflow doesn't include this capability. Some consider a value of 2.7 kilojoule per square meter and Kelvin in the sample of Novatec for thermal inertia per unit area of solar field. Thermal inertia depends on receiver material and could be detailing computed by software tool depending on material selection. Next slide, please. Receiver material selection, stress analysis and wall thickness calculation. Thermoflow allows the user to select different receiver materials. Carbon steel or stainless steel are available. And also pipe stress analysis and wall thickness calculation based on pressure operation levels. Some doesn't consider stress analysis as a limiting variable for linear Fresnel plant design. Incident angle modifiers. Three options are provided by SAM in order to compute incident angle modifier values. The first one is based on some position angles, zenith and azimuth. The second one is according to some incident angles, longitudinal and transversal angles. And the last one is calculated based on polynomial equation provided by collector manufacturer. Thermoflow only integrates the second options, calculating incident angle modifiers based on some incident angles. As improvement, we propose to integrate an analytica IAM models like First Optic Code or Monte Carlo model available in Soltray software within SAM or Thermoflow. Solar field parasitic losses calculation. Tracking power losses and piping thermal loss coefficients are explicitly input by user in SAM, not in Thermoflow. Turbine inlet temperature limit by receiver selective coating material. In Thermoflow, it's possible to limit superheated steam temperature, leaving superheated LF modules. SAM doesn't allow to fix this limit. Only field outlet design temperature could be provided by user as a reference. But under padlock condition, this temperature limit is superseded. Next slide, please. Next slide, please. Number of discretization nodes to compute energy flows in receiver pipes. Thermoflow defines a user input parameter to define the number of segments that should divide the receiver to calculate water properties along receiver length and heat losses. This parameter is very important to obtain accurate heat transfer coefficients, compressible pressure drops, and energy fluxes in receiver. Some identify number of boiling and superheating model with only one node. Parallel loops input parameters. In Thermoflow, it's possible to define different parameters for each linear Fresnel module or loops. For example, incident direct normal irradiation could vary from one loop to the other. Also, cleanliness factor differences between loops could impact in solar field behavior. All these facts cannot be modeled in SAM. Collector orientation respect to north. Thermoflow includes two parameters to define collector azimuth angle respect to north and tilt angle. In SAM are not programmed these two orientation options. Multi-tubes linear Fresnel configuration. Neither SAM nor Thermoflow allow to define a physical multi-tube LF model. Only polynomial equations to define heat losses or pressure drops are input by user to simulate this kind of solar collectors. Next slide, please. BOP modeling capabilities comparison. An innovative regression model to estimate annual plant performance. Sun integrates an innovative BOP model to reduce computing time for annual plant performance calculation. This model was not yet programmed in Thermoflow. BOP operation modes, startup, shutdown, standby, etc. Some startup energy take into account thermal inertia required to heat up receivers, steam material, and solar field headers, and also heating energy variation during transitory sun radiation periods. These heating energy flows are not considered in Thermoflow yet. BOP direct reheating LF modules. Sun doesn't provide these options for linear Fresnel power plants. Reheating improves power plant efficiency and unitary power output. In Thermoflow, direct heating could be modeled as well as indirect reheating with a heat exchanger. Condenser pad load levels. Sun better simulates air condenser real behavior. User can input number of pad load levels, and also a minimum limit vacuum pressure could be fixed. Thermoflow also offers offline condenser performance, but not allowed the two mentioned options. Balance of plant parasitic energy losses. Difference in balance of plant and solar field parasitic energy losses definition in both software are identified. More detailed information will be shown in the following slides. Air condenser fan power calculation differs in both tools. Due to the lack of information in condenser air stream properties, not permit to find energy flux difference. Next slide, please. BOP equipment performance curves for operation under pad load scenarios. During pad load condition, BOP equipment performance parameters vary with respect to nominal power conditions. These variations should be considered by some BOP regression model. Also, in Thermoflow, it's possible to achieve BOP equipment technology improvement analysis because all equipment performance parameters could be adjusted during annual performance calculations. Thermal energy storage integrating a linear Fresnel direct steam generation plants. Thermoflow integrates different equipments to model thermal energy storage system. This option is not considered in some for direct steam generation linear Fresnel plants. Solar field and BOP economic and financing models. SAM is the better tool to make an economical estimation approach for linear Fresnel power plants. SAM developed a detailed financial and economical models providing a very confident final renewable energy prices and cost, including U.S. government incentive and taxes to deploy solar power plants. Thermoflow cost model doesn't show the level of detail available in SAM, either includes financing framework or scenarios. Next slide, please. Reference linear Fresnel power plant. The comparison study between both software solutions was achieved based on the reference 50 megawatts gross power plant integrated by 26 Novatec linear Fresnel collector generating superheated steam with 90 bar pressure and 500 Celsius degrees temperature. As main conclusion, we confirm both software tools results are very similar for design point and for annual plant performance, as is detailed in the following slides. Next slide, please. Design point result comparison. Optical performance. SAM defines a variable called mid-track time. It's the time to compute plant energy flows at midpoint of operation. For this study, in order to compare both software capabilities, solar noon was calculated at 11:30, following some criteria for mid-track time. Regarding to collector incident angles, based on azimuth and sun angles, both tools calculated similar values are shown in the table 4. Next slide, please. In relation to real optical efficiency, main differences are detected. Thermoflow not consider collector tracking error factor. Either collector geometry effect factor either mirror reflectivity factor. All these correcting factors impact negatively in real optical performance. For this comparison, all those factors were considered unitary value to avoid any impact in final results comparison. Another difference is focused on the procedure in which some follow to calculate and losses factor impacting the incident angle modifiers values. Some consider that value included in incident angle modifier value, but Thermoflow calculates explicitly the end collector losses factor. Due to the listed difference, real optical efficiency value at design point differs slightly, as this is shown in table 5 and 6. Next slide, please. Thermal performance. Incident energy on collectors only differs in both software due to the criteria in dimensioning solar field aperture area. Sun imposed a value of 513.6 square meters for each Novatec collector unit. However, Thermoflow allows a flexible solar field dimensioning criteria for linear Fresnel collector units. Regarding to received energy is impacted by the difference in real optical efficiencies related before. A 2.37% relative error was detected in this study. Thermal power output from solar field. Energy flow to power block is similar in both cases. A difference only of 2%, mainly due to real efficiency discrepancy, was confirmed. Next slide, please. In spite of different methodologies between Sun and Thermoflow for calculating power cycle BOP energy production, final gross power results are very similar. Parasitic loads calculation methodology differs in the energy flows denomination, but the total value is only affected mainly for the difference in fan power results. Next slide, please. Next slide, please. Annual plan performance comparison. Despite the mentioned calculation methodology differences, annual total gross power relative error in gross power is 2%, and for net power only 4%. Conceptually, main differences are due to real optical difference efficiency and parasitic losses calculation methodologies. Next slide, please. In this slide, to finish my presentation, I'll summarize main difference between both software design tools. Next slide, please. Conclusion and purpose future work. I would like to summarize my main conclusion deducted from the comparison analysis and to propose future work development to improve and optimize linear Fresnel design according to this type of plant power output and real behavior. Operational behavior. Synergy between both software tool development will be a chance to improve SAM and Thermoflow capabilities. Solar field and BOP control and operational limits should be included in linear Fresnel leader steam generation software design tools. Simulation tools should consider low radiation days with different solar field and BOP configuration requirements. Reduce our order power block performance models for CSP plants, developed originally by Michael Wagner, was validated for digital steam generation linear Fresnel power plant in this study. Linear Fresnel optical performance simulation with analytical or Monte Carlo methods like first optic or salt trace could be programmed in thermal balance software tool like SAM and Thermoflow. A stress analysis limit should be imposed in thermal balance simulation software to obtain and optimize and feasible linear Fresnel leader steam generation power plant design. Thank you for my presentation. Thank you all for attending my presentation, and I'm available for answer your questions.